said, I'm Shannon Albeke. I work for WIGIS, the Wyoming Geographic Information Science Center. And I'll talk about my co-authors here in just a second as we move through this talk. Gracefully handling the information tsunami. We'll see if I've accomplished that after this talk here. So data management is a process. It's not something that's inherent and everyone knows. It's a process that we have to learn. And the idea of it is to efficiently store and organize data. So how can we use as little amount of disk space as possible? How can we organize it so that it's easy to use and we're reducing the duplication of information? It also is formatting the data correctly. So data are stored as a date time. Numeric is numeric. So as you run your computer algorithms, the computer knows what to expect and doesn't fail when it runs into some unknown value that it's not expecting. Annotation of data. This is an Achilles heel of many folks. How do we get metadata? Data about data. So that if you were to give it to someone else, they can understand and use the information just as you would. Data archiving and preservation. So how can we protect ourselves from messing up our own data? So how can we create backups? How can we save data that are 10 years old? How can we plan for dealing with data 20 years from now that we collect today? And I would say as researchers, we do a pretty decent job in these first four options of data management. The things we're used to, things that we've done, and we'll continue to do even better as new technologies arise. The one piece that we do not do a very good job of is providing accessibility to our data. So how can we share this information amongst ourselves? How do we break outside of our silos and share data across disciplines, as well as with the public, because many of you are interested in this information. So this whole idea of sharing of data has been motivated by the White House saying, hey, you need to make your data accessible if you get federal funding. NSF saying, you are expected to share your data. Publications saying, if you don't have your data available for download, you're not going to have your paper published in press. And just in general, open data advances science. We can share information and reduce redundancy of information, build on previous research, life gets better. So here, YK, you guys wrote this great proposal to get funded through F-Store, where we have fantastic colleagues here in the group that created research questions, they developed a study designed to answer the questions, collect the data, store it somewhere, process, manipulate, analyze it to create all these results that you guys are looking at. So YK data, you've seen how much research is going on and it's occurring. It's an elephant. How do we eat this elephant of data? It's quite large. It doesn't happen in one bite. But instead of pieces of meat, we're looking at pieces of databases, pieces of information that are within little silos of expertise, whether it's surface hydrogeology, tree transpiration, geophysics, isotopes, all these things. These are just a myriad of information that we are collecting here as a group. And it is our job to try to help all of our collaborators or colleagues here store and share this information as best as possible. So how might we deal with this elephant of information? Require some innovative approaches, things that, because we haven't been experts in dealing with this type of information and this quantity of information, what kind of approaches can we use to store, format, annotate, archive, and share all of this data? Well, it certainly doesn't happen with one person. We have a team. Team data management is what we'll call them today. Maybe you can call them by name, such as Dylan, who is a role player in being one, a grad student, and two, a newly hired person in ARC, which is the Advanced Research Computing Center, and is responsible for a lot of what I'm presenting today. And we have Samantha Ewers, who is the gatekeeper. If you collect data and you would like to have it be a part of the YK data system, it must pass through her to pass quality controls, which is a pretty neat thing in the sense that having a dedicated person to make sure data are correct is essential for this large scope of the project. And I should just know why, just since I'm also part of this project and that's where I work. So here's where the data team works. We are dealing with the data storage and the sharing and manipulation of information. So our needs for Albeke are, how do we store multiple types of data? We have tabular information, spatial, images, which could be rasters or pictures, discipline-specific formats, such as Steve Holbrook's work with all the resistivity and seismic data. Those are unique data files that specific software can work with, and it doesn't necessarily fit perfectly in some database, so we have to figure out ways of solving that. We needed to facilitate cross-disciplinary research. So how can we join disparate data types across space and time? How can we provide this system so that it's easy to try to coordinate research? We needed to provide the data security and the backup. So how can we, one, protect data from other folks, just jumping in onto a file server and messing around with data they don't know what to do with, so hackers might be one example of that. Secondly, how do we protect folks who collected their information and haven't had time to maybe produce their research and get credit for the work that they've done, so not getting scooped. And then we also want to protect it from ourselves. How often can we mess up our own data by deleting something on accident, sorting an Excel spreadsheet on one column instead of all columns? That completely destroys the information that you're after because the rows are messed up. How can we make this data discoverable and searchable? How can we decide, if you have this big pile of information, how can we look inside of it and figure out what is there, so that if I'm a new person, a new faculty, a new grad student, or one of the public, how can I determine what's in there without knowing the system offhand? And then obtaining this information. We need to do all of this. We need to make this data work. So this is our solution. We are using what I'm going to call or describe as a hybrid, where we're using both a database, an enterprise relational database on a server, and that is working in conjunction with a file server, where we store these project-dependent or research field-specific data types. Now, this really does a nice job of doing the storage, the formatting, the annotating, and the archiving of information. Our data are backed up every night, whether it's on the database or the file system. Our data are allowed to be searchable through the metadata that are stored in the database. This system is doing the things that we're already good at. It's providing this framework and infrastructure. And thus far, within the couple of years worth of data that we have, it seems minimal. I was a little surprised that we only have almost 11 million rows of data in our database at the moment. Seems small compared to how much research is occurring. But if we look at our amounts of files and storage that we have, I broke it down into above ground, below ground, and modeling data. And we have two categories of processed and unprocessed. Processed data are what is available right now within our database that you can search. Unprocessed are data that people have collected, and we haven't gotten it into the database because the researcher says it's not ready. So 3.5 terabytes of unprocessed modeling data, 2.9 terabytes of processed modeling data. So this is all the stuff that Brady's doing, or Nori. Above ground data is like the tree transpiration, the surface flow, all this information. It's there. We have lots of information that can be obtained and used by all of our colleagues here in the room. So how do we share this information? So we've done our 4 pieces of storage and archiving and whatnot, but how do we share it? And the obvious method is to use the web. And I don't know this, I just threw this figure in because I thought it was intriguing. What it is the number, as of September, the number of websites Google has indexed. And this is saying that Google has indexed almost 47 billion websites in the world. Holy buckets, how are you supposed to not get lost in the sea of information? And so for us to help our users not get lost in the sea, that is the internet, we needed to come up with methods to help us search this information. So methods of data discovery. And we chose a geosemantic method. So what does that mean? It means we're going to use a spatial component, so maps. We can search for data using a map. Most data can be georeferenced. I always say all data are spatial. That is my mantra. And in this case, we are applying that. We're going to use contextual text searches. So instead of typing in a traditional keyword search within the database, we can have it meaning, have your word have meaning. So flow would mean stream flow. So it can be smarter about finding your information. And of course, searching through time, because time matters. Space and time are pretty important. Using these three ideas, we're going to create a fully integrated, or we have mostly created a fully integrated system that allows us to use a web server, so a website, that speaks to a map server, which has the geolocations of all data that we have collected thus far. And that map server and web server can speak directly with the database and the file server to provide access to all the information that we have available through searching. The website is in alpha right now. Most people haven't heard of that. Beta is where we get to test things. Alpha is a step before beta, which means there's still things that are broken. But we're working on making it be the beta, hopefully by the end of the calendar year. So this website thus far, even though it's only been out for a couple months, 5 months now, we've had approximately 265 sessions. What does that mean? 265 times people logged on to the database and tried to find information. And we've had 80 new users, so approximately 16 new users per month. So this is helping us get some feedback to make our tool a little better. Hopefully it's some folks here in the room. So what are the advantages of us using this web-based approach? Well, web services allow us to access this data anywhere. That's the obvious one. The second obvious one is platform independence. It's a web browser. Regardless of what machine you're using, operating system, all web browsers should be able to use this. It provides security for the researchers who are collecting this data, because logins are required to get data that are brand new. So if you have stream gauge data that's feeding directly into our database, which we hope to have occurring here in the near future, if the data aren't a year old, you're not able to see the data. But if you have a login, you're authenticated, we trust you, that you can see this new data and you're not going to be nefarious with this information. You can see live data as it's occurring in the database. So that means new data are available immediately. Something that sort of people who develop applications, the nerdy folks in the room, tool development is focused, meaning we're not trying to build a one-size-fits-all application. We're asking specific questions of the data and can provide specific pieces of that information in a directed manner, which is, from a programming standpoint, is much nicer than just trying to be all things to all folks. And web services can be shared. We can provide exposure to pieces of our information, and other people with other websites can use our data dynamically. So that's a nice advantage of the web service. So what does it look like? Well, currently it's a simple map with a web service for points in space where data exists. So if we were to do a spatial query, like these highlighted points, we selected those. It's now telling us what information at those points are available. Poof. Pretty easy tool to use in this case. Once you have selected a site, you can preview the information. All of a sudden it tells you the metadata. So here you can use it yourselves. You can see what each column of data represent. You can see the dates at which we have existing data for those sites. You can filter on those dates. You can export that information to an Excel, a text file. You can export the spatial components. So where in space can I get those points in space? We have 1 point, 500,000 rows of data were collected at that one point. This is going to allow you to get both of those pieces of information. I think it's pretty cool. This is neat. This is useful. This is providing a platform that is flexible and can handle all types of data, whether it's tabular or aggregated data like resistivity and seismic. So what do we need to do to finish this up so that all of you can use this without any issues? Well, first of all, we need to solve a couple problems. One being, did you know that web browsers and web pages reduce the number of rows you can return in a spreadsheet or a text file? I didn't until we tried downloading 300,000 rows of data, and it breaks at about 120,000. So we're trying to solve that problem. We have a solution in mind. It's just a matter of finalizing that implementation. Making sure that our spatial data sets work every time. We're going to use well-known text. So it's going to be a text file to deal with space. It's pretty cool stuff, because that's open source. Open Geospatial Consortium says that's a way to go. Don't use an Esri shapefile, use a text file. And we want to fully implement our semantic search tools so that we can provide not only a spatial method for finding data, but type in the type of data that you would want, and it will show you all the pieces of information that match that criteria in context, not a straight keyword search. And a university-wide initiative that also has an effect for other folks around the state, not just the University of Wyoming, is we need to expand our data storage infrastructure. As I mentioned, if we archive data, it's pretty easy to archive data from an existing project because you have money to deal with it for that 5-year period. But true archiving and what NSF expects is for you to have this data available in perpetuity. How do you plan to store this data for 20, 30 years and make it available and searchable and downloadable? I think we're coming up with a solution as a whole, as a university. It's going to be called the Archive. That's a handy little nickname, I like it. But it's still not fully implemented, and we don't know all the policies and how we're going to fund this in perpetuity. The third piece is develop additional web services that help meet national data sharing standards. Some of you may use Quasi for obtaining extra data. We are going to serve out our information from our database, our storage facility that meet Quasi standards and will be searchable and discoverable within that framework. It'd be nice to integrate our application with other applications, such as Words. I was just talking with Chris Nicholson about this. They have a great mapping application with lots of ways to find and discover information about the state and water. We have some similar information, but of a different angle. How can we make these two applications talk and share information between each other? Should be somewhat simple, given they're both web services, but there's always some devil in the details that we'll have to work out. And finally, I think it'd be fun, useful, and interesting to develop what I would like to call analysis modules, where we write reusable code that sits on top of any application that would allow us to, say, plot data. I see stream gauge, and I see it has dates. I want to plot that through time. How can we provide that access, that dynamic way of visualizing information that we've collected in a dynamic manner so that you can change how that graph looks, use it as an educational tool. Wish we had things of science posse still around so we can create student learning objectives that can be applied to 6th graders, 12th graders, and use this data as a way of describing information that they can learn to interpret through some type of teaching. Also combining, it's really actually fairly difficult at times to combine data through space and time of disparate types. The system is made to do that, but for non-experts who don't know how to do that, can we provide the tools to help facilitate that process? Don't know yet, it's worth trying, but that's where we'd like to go. And with that, I I will not bore you anymore with data speak, and I'll take any comments or questions.
One question while we're queuing up the next.
Ginger.
Well, I know you mentioned this briefly, but the linkage of the Albeke database with the words data server. Is there a time frame for making those two talk?
Well, it was just brought up in discussion today.
So perfect. So tomorrow will be fun.
That's how it always happens. It would be great if we could move forward with something like that. And I know that folks at YGIS would be happy to work on something, but it just doesn't magically appear. So if we could find some funding or ways of making that happen, that would be excellent, and would be fun to do as quickly as possible if given the guidance and direction.